As I've already said, there are two broad topologies for clock distribution: the tree-based distribution and the mesh-based distribution. So in this lecture we'll take a more detailed look at the mesh-based distribution. So what is a clock mesh? As you can see here, the mesh is just a horizontal and vertical arrangement of wires. This we call it as a 2 by 2 clock mesh, and these are the clock sinks denoted as cross marks, and they can be just directly connected to the mesh, and the mesh is driven by buffers at these nodes, which we call it the mesh nodes. So the intersection of the horizontal and the vertical mesh wires, and the mesh buffers are in turn fed by top level tree. So typically the clock mesh is never used as a standalone method of distributing the clock. So the mesh is always used with the tree. So often it's called the tree driven mesh. Instead of just being called as a clock mesh, it's also called a tree driven mesh. So we have the clock from the PLL distributed through a top level tree and reaching the mesh buffers, and from the mesh buffers it gets distributed to the clock sinks or the flip-flops. So the mesh-based distribution has received much attention in the recent years since 2010. Now this is further explaining the same mesh-based distribution, that even from the mesh, so this we have got the mesh here driven by a H tree, two levels of H tree at the top, and then these the H tree leaf nodes feed the mesh, and from there, from the mesh also you can have uh, local trees. So that is just to say that we might use another level of tree after the mesh, or sometimes the clock sinks are directly connected to the mesh itself. So briefly reviewing the differences between the tree and the mesh. In the clock tree, we use some combinatorial algorithm to construct a zero skew tree with minimum wire length and power dissipation. But often the problem with the tree based distribution is that they are not resistant to skew induced by process variations in deep submicron technology, because you know that fundamentally the difference between the tree and the mesh is that in the tree you have a single path from the source to the sinks, while in a mesh you have multiple paths. So because of those multiple paths or redundant paths, the mesh is more resistant to skew induced by process variations. In fact, that is one of the most important advantage of mesh based distribution, which makes people consider mesh as a viable alternative to tree based distribution, but not without a cost. As you have seen, when we have a mesh based distribution here and here in the mesh, we end up using more wires. So we end up using more wires, hence more wire capacitance, and hence more dynamic power dissipation, because every time period the clock has to drive the whole mesh capacitance. So the dynamic power dissipation CL VDD square F increases. The other important thing is that the mesh simulation of the mesh, before we implement it, we try to simulate it using a SPICE tool to study the clock latency, skew, and the slew of the clock signal, is difficult because the Elmo delay model cannot be applied. If you recall, Elmo delay model was originally proposed only for a tree, for an RC tree, and Elmo delay model cannot be applied to a mesh. So as I said, that in a mesh based distribution the most important challenge is the power. So we have to minimize the power dissipation. So that is an important topic of research. Another important topic of research is the is simulation tools or automation tools which will automate forming the clock mesh and simulate it. And mesh simulation is actually computationally very intensive. We'll be looking at the reason in the next few slides. So when we talk about mesh synthesis, it's basically about forming the mesh. And when we have to form the mesh, the first important question is how dense the mesh should be. So here you can see for the same arrangement of sinks in cases A and B, the right hand side shows a more dense mesh compared to the left hand side. But you can also see that in the right hand side the stub lengths are small. The stub is that small wire segment connecting the clock sink to the mesh edge. And so I have defined the term stub here. So it's the small segment connecting the clock sink to the mesh edges. So if the mesh is more dense, the stub length is less, which means your skew also will be less. So here you can see that the mesh is less dense and you have stubs of different lengths. So you'll have some skew introduced in the mesh, because actually in the mesh we'll make sure that the clock reaches all the mesh nodes wherever the buffers are placed. We'll make sure that the clock reaches the mesh nodes at the same time by basically forming a zero skew tree above the mesh. So you can see that the top level tree, and this top level tree will be designed for zero skew, with these mesh buffers being the points at which the clock arrives with zero skew. So you can understand that the clock will be reaching all the mesh buffers at the same time if you have designed a zero skew clock tree above the mesh. But from the mesh buffers there will be small differences depending on the stub length. So this will achieve a better skew. So that was what this research work proposed, a uniform mesh where the mesh is recursively made more dense and dense till you achieve a target skew, say a target skew of say 20 picoseconds for a 1 gigahertz clock. But the problem is that if the mesh is made more dense, we'll have more power consumption because we're using more mesh wires and hence more capacitance to be clocked at for every time period. And another researcher in this paper, ACM Transactions on Design Automation of Electronic Systems, has proposed a skew driven mesh, but skew driven meaning that the mesh density is repetitively increased till you achieve a target skew. And the only improvement being that it can also be made non-uniform, where having formed a uniform mesh, the author proposed moving the vertical horizontal wire or the vertical wire closer to the sinks so that the skew can be minimized. But having said all this, if you look at a real case, this is the ISPD 2010 benchmarks. ISPD is International Symposium on Physical Design, and when they had the clock network synthesis contests in 2009 and 10, they have released these benchmarks which were from real Intel designs. And this is one benchmark where you can see that the distribution of capacitance, these dots represent the clock sinks, and in the benchmark, in the file accompanying this figure, they have told what is this individual capacitance at each sink, and you can see that the distribution of clock sinks is really non-uniform, and even the load capacitance was varying. So these ISPD benchmark 6, 7 and 8, supposing if use the skew driven mesh, forming a uniform or a non-uniform mesh would be inefficient because you end up using more wire. So I have proposed a capacitance driven mesh formation methodology, which is basically forming a non-uniform mesh according to the density and the capacitance of the sinks. So as I already said, the individual capacitance are not all same. So it was in this benchmark, it was varying from as low as 4.25 femtofarad to 50 femtofarad. Okay, so I proposed a methodology of forming the mesh which is called the capacitance driven mesh. So here I've just shown the left half of the ISPD 6 benchmark, 2010 benchmark number 6. You can see that this is that dense region which I showed in this previous slide. So for this dense region, so the mesh is made more dense in this region, and where you have very few capacitances, very few clock sinks, the mesh is made more sparse. So how this was done was to take the entire benchmark and calculate the total capacitance and then split it into two halves, and the capacitance gets reduced by half, and then keep into recursively partitioning the individual rooms into sub rooms till the capacitance in a particular room reaches a particular target. So we took it as 100 femtofarad. So we would repeatedly partition the clock sinks into rooms, or make it more dense till the capacitance in each room of this mesh reaches 100 femtofarad. So the density of the sinks and their individual capacitance was taken into account to form this mesh. That means just because you have more sinks, the mesh will not be made more dense. So the number of sinks and the individual sink capacitances are added and then found out. So this is a very efficient way of forming the mesh. So having formed the mesh, we'll look at how the mesh can be simulated, because we have to simulate it and study the clock latency, skew, and the slew. So we use the pi model of the wire. So when we use the pi model of the wire, the mesh will become like this. And when we use the ngSpice tool, there is this URC command, which is basically uniform distributed RC model of a wire. So in ngSpice, if you just say URC and length is equal to say 10 nanometer, it will automatically calculate for 10 nanometer what is the resistance based on the process parameter. You would have told that resistance per unit length is so much ohms per micrometer, and the capacitance per unit length is so much femtofarad per micrometer. It will calculate and form this pi model. Now when we consider simulating a clock mesh, we have to simulate the clock mesh to know the skew and the power dissipation. This is a very difficult task, a very time consuming task. In fact, the difficulty in simulating the clock mesh was the reason for its unpopularity till recent years. And there had been cases of HSpice tool, which is a very efficient tool from Synopsys, even HSpice tool hanging up when they tried to simulate a clock mesh. And so what people have proposed, these two researchers or research groups have proposed a sliding window scheme to simulate a clock mesh. The sliding window scheme is basically a scheme to split the entire mesh into windows of reasonable sizes, and those windows are modeled accurately. So here we have this being the entire mesh split into 4 windows, and inside this window the mesh wire segments are modeled like this pi model, and each bit of this wire, so you can see two clock sinks S1 and S2, and connected like this by a simple tree to this mesh edge. So this segment has to be pi modeled. Every time there is a divergence here, so here the clock comes like this and gets distributed to S1 and S2. So again, from this point of divergence, the wire, that small bit of wire to S1 and that small bit of wire to S2, those also have to be pi modeled. So you can see that in a real case where you have, ISPD 2010 benchmarks had clock sinks of 800 to 1000 clock sinks, and if you're going to do an accurate modeling of the entire mesh and simulate it, it's the simulation is going to be intensive. You might need more RAM, and as I said, there might be cases of the spice tool hanging up because you typically have thousands and ten thousands of mesh segments to be pi modeled, and so the sliding window scheme comes to help our rescue to our rescue by doing this. So what we do is, outside this window, the wire segments are pi modeled, but those mesh the stubs are approximately modeled in the sense that this capacitance inside a room is lumped to this mesh node, and this wire resistance is neglected. So that is approximate modeling. And so what we do is, a big mesh is split into 4 windows, and inside this window we do an accurate modeling, and outside this, the other 3 windows, we do an approximate modeling, and then we simulate this whole mesh. And then during that simulation we find out the clock latency to all the sinks in this window, and then we move this window up. That's why it's called the sliding window scheme. So in which you will do an accurate modeling inside this, and do and approximate modeling outside all those 3 windows. So that is the sliding window scheme, and in fact they have the research has shown that the delay calculated by the sliding window scheme at the clock sinks is only there's only 1% difference when compared to the golden simulation, where the entire mesh is accurately modeled. Now I come to buffer placement. The buffer placement is a crucial step in the design of the clock mesh distribution network. The buffers have to be placed at the mesh nodes. The buffers are not placed at all the mesh nodes because that would be really inefficient due to the power and the area consumed by the buffers. So we don't have to place the buffers at all the mesh nodes. The mesh node is the intersection of the horizontal and the vertical wire in the mesh. We don't have to place the buffers at all mesh nodes. That will be really inefficient. So people have come up with buffer placement algorithms where we have to decide what are the mesh nodes in which I have to place the buffer so that the clock is able to reach all the sinks with the reasonably same latency or minimum skew. So the principle involved in buffer placement, the basic principle of placing the buffers, is to place the buffer at nodes so that the buffer will be able to drive the capacitance load around that mesh node. So if I place the buffer here, it should be able to drive the capacitance around that mesh node. So again, people have proposed many algorithms. One of the easiest way is to just start from this, we may say this is the origin, and go through these rooms and find out the capacitance and find the capacitance centroid and place the buffer at the mesh node closest to the capacitance centroid, because the capacitance centroid may not be always at the mesh node, so we can place it at the mesh node closest to the capacitance centroid. In fact, that is what we have proposed. I have proposed in my work, and this is the same mesh after buffer placement. So you can see that these circles are buffers placed on this mesh node, these small circles. So you can see that in this region, where you have a dense location of flip-flops, you can see that there are more buffers placed, almost at all the adjacent mesh nodes. But you can see that where there is dense location of clock sinks, the buffers are not placed at these mesh nodes because they are not needed. So basically this is capacitance centroid method, where we calculated the capacitance centroid of the sinks and placed the mesh node. Supposing for this small room, the capacitance centroid comes here. It just placed at that mesh node closest to the capacitance centroid. And supposing in some places where there is a capacitance centroid closest here and also here, and so you have to place two buffers, what we have to do is we just add the buffer capacitance and place a bigger buffer there. So what do I mean by a bigger buffer? I'll discuss when I discuss the buffer library. So what is a buffer library? Just like any standard cell library, we have a buffer library, which is basically a collection of buffers of different sizes to drive different loads. So because as you can see here, we don't need a buffer at all nodes. That's the first point. The second point is we don't need a buffer of the same size. So if the capacitance load is say 100 femtofarad, we don't have to place a buffer which can drive 250 femtofarad. The buffer will be big. We are wasting the area, so we have to be as optimized as possible. So we have to design a buffer. Now when we design a buffer, we must make sure that the power dissipation due to the short circuit current in an inverter is minimized. You know that in an inverter there is a small duration, a small transient time in which both the PMOS and NMOS is on, and in that small transient time you have a direct path from VD to ground and you have a short circuit current. And one of the ways to minimize the short circuit power in a CMOS inverter, when you have stages, was proposed by Harry Windrich, and what he says is if you have to minimize the short circuit power dissipated in this buffer, we have to make sure that the rise and fall time of the clock signal, the slope of the clock signal, must be the same at all the points in this circuit. So if we feed a clock here, if the rise time is 100 picosecond, the fall time here must be 100 picosecond, and the rise time here must also be 100 picosecond. So we use this principle to design a buffer. And as I already said, the buffers are placed at the mesh nodes according to the density of the sinks in its vicinity and their proximity to those sinks. So that's why we use the capacitance centroid method. And typically, because you have thousands of clock sinks, even the buffer sizing and placement is automated. So what I mean by that is we use an algorithm to find those crucial points or the mesh nodes at which we have to paste the buffers, and also what is the size of the buffer to be placed. So that is also automated in the sense, according to the load around that node, we have to place a buffer. So we design a buffer library like this. So this is a buffer library. These are the 8 buffers, B1 to B8, and B1 can drive load up to 50 femtofarad with a slew of 100 picosecond. So that's the meaning. B5 can drive a load up to 250 femtofarad with a slew of 100 picosecond. Right? That means when you have a 250 femtofarad load, if you put a B5 buffer, it will be able to drive it with the required slew, the rise time being a slew of 100 picosecond. Okay, so for a 250 femtofarad load, we should not put inappropriate buffer. For a 250 femtofarad load, we should not put a B2 buffer. If you put a B2 buffer, it's going to slew. The clock is not going to rise in 100 picoseconds, it's going to take 200 picoseconds, which will affect the functioning of the entire circuit. So this is the first inverter W by L and second inverter W by L. You can see that they are designed for 45 nanometer, and the WP by WN is almost 1.4 to make sure that the rise time and fall time are the same. So that is the buffer library design, and once you design the buffer library, 6 or 8 buffers, you can put them at those mesh nodes according to the load. So each buffer is designed to drive its load capacitance with a particular slew constraint. So these buffers are designed to drive those loads with a 100 picosecond slew. So by this way, we'll be able to make sure that the clock reaches all the sinks with the slew constraint, with the slew not being violated, and hence we'll be able to have an efficient mesh. Thank you.